Today we are going to discuss about solving Cauchy initial value problem for first order linear PDE. Linear or it can be semi-linear, because the form I have taken here you can easily understand it is a semi-linear PDE because C, X, Y, U is here. Okay, C is the function of X, Y and also U is in here. So it makes this differential equation, whatever partial differential equation are written, as a semi-linear partial differential equation. And A, B are continuous differential functions of X, Y. That means I am considering all the analytical properties which are to be satisfied, because right now I am considering the Cauchy initial value problem has a solution, and we are trying to find out, or rather interpret, how to bring that solution. Okay, this is the initial data which is provided. X is some function of x0, x is function of eta, y is the function of eta, u is the function of eta. Okay, so this x equals to x0 eta, y equals to y0 eta. Actually, what it gives? It gives initial datum curve. I write like this: initial data or datum curve. Sometimes we say data curve. Let me represent it as say gamma. Okay, and what will be the value of the solution? Is it is given by this u0. So the solution will satisfy this thing. So we already know if we want to satisfy, just find out the general solution of this given differential equation PDE, then what will come? You will get actually a family of surfaces, solution surfaces. So any surface, any solution surface is said to be an integral surface of the PDE which you are solving. Okay, so actually we are going to get a family of surfaces, but when we specify this data curve, this gamma, then what will happen? We will get we'll pluck one of the family members from that solution surface family. Okay, so we will try to do that. Okay, so before doing that, let us try to understand whenever u is a function of xy, right? Now if you consider any vector a which has two components a, b, that means I am considering this vector in the xy plane, okay, along with the direction ratios this a, b. Then if you want to find out the directional derivative of u along alpha, what we will get? You will get direction derivative u along alpha. If I want to do, then you will get ux dot component of alpha along a plus uy dot component of alpha along y. Okay, so this gives you the direction derivative of u along alpha. But if you just note down, this is nothing but the left hand side of the given equation 1. Okay, so the directional derivative of u along alpha is present there in the LHS of equation 1. That helps us to do what? You consider any curve, okay, such that any curve, say gamma, such that at any point, say pxy on the curve, at any point, say pxy on the curve, tangent to the curve is given by this alpha to the curve gamma is given by alpha. So that means what? If it is given by alpha, what can we say? Achha, for that, we just take the help of parametrization. That means what? I am considering gamma. We know we can express any curve in terms of parameters, so that we can say we are expressing the curve as a parametric curve. So here I consider gamma to be like this, where sigma is some any real number. Okay, so you can easily understand if this gamma is any curve which has tangent along alpha, and alpha has this as these components a beta, a b, then what can I say? I can say the variation of x and y along gamma as this a, and dy d sigma as b. Okay, so you can easily understand if from here I can bring out dy dx is equals to p by a, and if you solve it, this is actually first order ordinary differential equation. You solve it, what you get? You get a one parameter family of curves. Okay, and you can easily understand up to the semi-linear equation which we are saying, this a, b are only functions of xy and never it will be a function of u. So this dy dx you can easily say it is, you will easily get this equation b by a, it will only contain xy. So once you integrate it, you will get a one parameter family of curves in xy plane. Okay, this family of curves has a specific name. This is called characteristic curves of the PDE which you are solving. Okay, the characteristic curves, and sometimes we say these equations dy dx, this is characteristic equations. Their equations I'm writing in short. Okay, characteristic equations. Okay. Now you can see here, once you use this characteristic curve, I can say what along the curve, let us see how this u is varying along the curve, along gamma, along any of these gamma, because you are getting a family of curves. You can consider any of these curves and try to study the variation of u. Okay, and as we are trying to find out the particular solution, we are not considering the general solution. We are just trying to study some of the properties so that I can use that property to find out the particular solution surface. So along the curve, variation of u along curve, how it will get it? It will also vary with sigma only, because sigma is the parameter which is regulating the curve. So du d sigma. And how do you get du d sigma? Again, del u del x. Like this. This is the chain rule, simple chain rule we apply. Then we are going to get a ux plus b uy, but according to the given equation, it is nothing but cx by u. So ultimately you are getting du d sigma is equals to cx by u. This is called the compatibility condition of the given PDE. That means you are considering some curves, and along the curve, how your solution surface is varying, that condition is said to be the compatibility condition. Okay. Achha. So up till now, we have find out how the curve varies, or sorry, how the solution surface varies along these characteristic curves. So as I am saying, for the semilinear or linear PDE, what is happening? We are getting characteristic curves are nothing but some curves here in the xy plane. I consider this as x, I consider this as y, or you can revert also, and this as the direction. Okay, this is the origin. So these are all the characteristic curves. Okay, and along the curve, the sigma is varying, because every curve is a parameter depending on the sigma. So along the curve, the sigmas are varying. Now let us use, or let us consider the initial data curve. Which is the initial data curve? As we have already said, this is the initial data curve. This one. Okay, this gamma one. Okay. So now you can see this is a curve, and again you have obtained a family of curves. Okay, so if I consider this, let me write it down right here so that it will be easier to say. X equals to some x0 eta, y equals to some y0 eta, the xy part if I say. So you can easily see, and along this curve, along gamma, u is taking, or expression like this, u0 eta. So this is some curve. And as we have said before, for the Cauchy initial value problem, a solution to exist, what we need is this curve gamma, and should be nowhere tangent to any of these characteristic curves. So right now I consider that condition is maintained. Okay. Now, if this condition is maintained, that means what? This one will cut all the characteristic curves. So this one is your gamma. Okay. And every one of this is your capital gamma. That means every one of this is your characteristic curves. Okay. So what you can see from here, at any point which is cutting, say this one is point P1, this one is point P2, and likewise it goes on and on. So at any point, if I say P1, okay, so P1 is the point of intersection, so it is common to both the curves. That means it should satisfy this one, and also it should satisfy capital gamma. That means this one, okay. So that means it should satisfy this equation also, this differential equations, because this is ultimately characterizing this gamma only. Okay, so that means what can you say? From here, I can say I am having dy dx as some first order ordinary differential equation, along with it some initial conditions, x equals to x0 eta, y equals to y0 eta. Okay, so that means from here I can solve rather to get x as some function of sigma n eta, y as some function of sigma n eta. Okay, and again you can see this eta is dependent on this x0 y0. I will use this x0 y0. Right now I am just focusing on the parameters. Okay, sigma n eta. So that means what you are getting, you can see here, as you move along the curve. Another more important thing I should mention here, this curve is cutting, right? Let me draw it again here. So any one of you consider only suppose I consider 3 just for sake of explanation. So this is my initial data curve gamma, and any of this you are considering, see this one gamma, here also gamma, because it's a whole family of parametric curve. So as gamma is varying, we say the word initial value problem, right? As I already said in one of the previous lectures, we say the initial because we consider it as a physics motivated problem. That means when we are starting the initial condition, we consider a time equals to 0 conditions, right? So as to match with any dynamics problem. But as you are considering mathematics, you can consider any value as any particular condition, not only initial condition. We just don't need to stick to the condition, initial condition. But for the sake of convention following, I am saying right now I am using initial value problem as a terminology. So initial conditions as the gamma related properties, whatever gamma related properties are given, I am saying to be initial data curve also, just for that nomenclature. Okay. So what we see is gamma, capital gamma, along any of the curve, sigma is heading, and you are getting the plot of this, right? So I consider, let me draw it properly. So suppose this is your gamma. Okay. So I consider this point of intersection as a point where gamma just starts moving. That means sigma equals to 0. Okay, not that starts moving, but you consider this as conventionally sigma equals to 0. Again, the convention is taken in support of the initial value condition, initial value problem thing. Okay. Otherwise, we could have taken sigma equals to any value, say sigma dashed. Sigma equals to sigma dashed, or sigma equal to sigma 0. No need of taking sigma equals 0, just for the sake of, yeah, you can easily understand if you take sigma equals to 0, then when we'll do the problems also, this will simplify a bit. Okay. So whatever, you take a particular, the main thing is you take a particular value of sigma. Okay. So as soon as you take this, as if, the idea is like this, as if from here sigma equals to 0, and then it starts changing, sigma equal to say 0 0.1, 0 0.2, 0 0.3, like 1. And you are getting the curve, characteristic curve. Same is the case here. Same is the case here. So what is happening, along any of this curve, you can easily see sigma is varying, starting from sigma 0. Okay. But as you move along the curve, what is the condition over eta? Eta is remaining fixed because eta characterizes this curve, and this curve is varying like this, and this curve cuts here at a specific point. So eta here, eta here, eta here, it changes like this. But as I move from this point to another point, eta will remain fixed. So that means I say my sigma is varying along the direction of characteristic curve. So along direction of gamma, and eta is varying across gamma, across family members or across members of gamma. That means you go from one member to another member, from here to here, eta changes from, say, suppose eta is equals to, let me use another color so that you can easily understand. So along this, eta from here, eta is value, say, so 0. Eta 0.2, here eta 0.5, like that. So you are moving from one curve, one characteristic curve, to another characteristic curve, to another characteristic curve, to another characteristic curve. Point of intersection is changing, obviously, and that is you are changing along the initial data curve. Okay, so as I said, eta is changing across the members of gamma, and gamma is changing along any member of gamma. Okay, sorry, not gamma, my mistake. Sigma is changing. Sigma changes along any member of this, and eta changes across members of this. So quite obviously here it remains constant as you move along any member, and here sigma remains constant as you go from one curve to another, because as I said here all at all these points sigma is having the value 0. Here sigma equals to 0, here sigma equals to 0, here sigma equals to 0, like that. Okay. So ultimately I can say my x and y coordinates, x and y are ultimately becoming functions of sigma and eta. How? Using the characteristic curves and the initial data curve. That means using, I'm writing in short, curves and initial data curve. Okay. So as you can see, as sigma is varying along the curves, eta is the one which is giving you one after another family members. That means you vary eta, you get one after another family members. So we have removed the C, and that arbitrariness, that is getting one after another family members role, is played by this eta now. Okay. Okay. So we have seen how this we can write the x and y. That means any point p x y. How can we write in this form? Okay. Now let us try to find out the solution, the particular solution U, such that it satisfies the given initial condition. Okay, so if you just recall back, what are the initial conditions? This was like the curve along with U taking the value or taking the form like U0 eta, some function of eta. Okay, so for that, let us consider this figure again, where we are considering this one, where suppose this is the xy plane. So here later the curves, any of the characteristic curves are like this, and this is our initial data curve. So as I already said, these are the points where we are intersecting P1, P2, and likewise. Okay, so let us consider a single one. Okay, that means any one of this where you are intersecting. Say I consider P1 as the point x1, y1. Achha. So what is our task now? We are trying to justify that indeed such a unique solution exists. That means indeed we will get some U, a specific or particular solution surface will exist. I will just justify that first. Then we will just see what is the strategy in general to find out such a solution surface. Okay. So particular solution surface existence first we will guarantee, then we will show the strategy. Then how can we find out the particular solution surface? Okay. And then once we do some sums in some later lecture, then it will be clear exactly how we are going to deal with this Cauchy initial value problem. Achha, right now, once you just recall back, we have the characteristic equations, we already derived it, right? Dx d sigma equals to A, dy d sigma equals to B, and compatibility condition du d sigma equals to C. This function of xy, this function of xy, this function of xy and u. Now, along with this, as I said, I am considering a single curve, or as just I am saying, specifying or isolating it rather, just to make the idea a bit clear. This P1 say, and the point say x1, y1, and this is your characteristic curve. That means one member from this capital gamma, and this is your initial curve. Okay. So now you can see if because of the initial condition, this one is provided with this initial condition, this one is provided with this initial condition, and this one is provided with this initial condition. So if you recall back whatever we have learned in the theory of ordinary differential equations solutions existence, you can just check if those conditions are satisfied here. Because why? Because we already said A, B, C, all these are functions, continuous differential functions. That means belonging to C1. Okay. So that means if you consider this one particularly, then it has a unique solution. Unique solution in terms of obviously in sigma. Again, it has a unique solution. And the same is the case for this one. It is also a unique solution. So ultimately, actually, we are getting here solution of this form ki x equals to x0, y0 and sigma, y again sigma, and u will is any curve, oh sorry, not curve, my mistake. The solution surface such that u takes this on the curve. Okay. So once we get like this along the curve, that is along the characteristic curve, this will be the solution. Okay. So this is becoming fixed. You are getting a particular solution surface. So right now we prove the existence of the solution surface. So what will be the strategy for finding them out? The strategy will be ki I already said ki x1, I am taking the point of intersection as x1, y1. So this is a point which is common to gamma and gamma because these two curves are intersecting. Okay, and now right now I am writing this capital gamma means I am just writing any of the characteristic curve member. Okay. Now once I take this, you can see from here, since it is on gamma, that means I can write x equals to x1 equals to x0 for some eta dashed. Okay, again y equals to y1 equals to y0 for the same eta dashed. Okay, also as x1 is lying on this any of this curve, and already we have said before ki you can write any of the point x as sigma eta function, and at the point of intersection this x sigma equals to 0 comma eta. So here eta equal to eta dashed. Once I am considering x1, that means I can write ultimately 0 comma eta dashed equal to this. Similarly y1 equals to y 0 comma eta dashed. Okay, so from here we can see you can easily eliminate eta dashed. Okay, and also there is a u, here u0 eta dash at the point of intersection. Okay, so ultimately from this three, that means ultimately you are solving the characteristic equations and the compatibility condition you are using to find out the solution like this. The format of the solution goes like this: ki x is a function of x 0 eta, y 0 eta, and sigma obviously. Y is a function of x0 eta, y0 eta, sigma, comma, and then we will just rub it out and write it specifically. This is comma, sigma, and u will be given by u0 function of x0 eta, y0 eta, u0 eta, and sigma. Okay, so this is the solution surface which we were trying to find out using the for the Cauchy initial value problem, the particular solution surface, satisfying the initial attack of, that means it is lying in neighborhood of initial data curve gamma. Okay, and as you can see, it varies along any characteristic curve as prescribed by the compatibility condition. That means it varies by amount c, x, y, u. Okay, So what we need to do? We need to first find out the characteristic equations, then solve it, okay, to find out the one parameter family of curves, okay. Then you use initial data curve there so as to find out the point of intersection in terms of sigma and eta, and then you eliminate this eta. And once you get these things by eliminating eta, putting sigma equals to 0 at the point of intersection, you get eta dash replaced, okay. Then you can find out x in terms of x0 y0, as I said, in this form exactly, x in this form, y in this form, and ultimately u equals to u0 in this form via solving du d sigma differential or linear differential equation. So this is the general strategy for finding out or rather solving Cauchy initial value problem. This idea will be more clear once we do some problems over it in the next class.